Oh, and let's see you again. And let's start our lecture on avionics engineering. Today we have lecture number 19, avionics system integration. You know, major avionic systems generally comprise a number of smaller subsystems, which are combined to form an overall system. The combination, interconnection, and control of the individual subsystems so that the overall system can carry out its tasks effectively is referred to as system integration. The number of subsystems which need to be integrated to form a major system can be appreciated from the previous lecture on flight management system. It is instructive to review the development of avionics systems and their integration into overall systems in the light of the technology available and the circumstances prevailing at the time. The object is to put the development of today's advanced systems and the even more advanced systems currently under development in perspective. In many cases, the current concepts and philosophy are not new. Often the originators of particular system development in the past were far cited in their concept, but as always were limited by the technology available at that time. World War II resulted in a major growth in the electronic equipment installed in aircraft and the birth of avionics, with the very rapid development of airborne radar systems and associated display radar warning systems and ECM, and more advanced autopilot systems exploiting electronics. Installation of the electronic equipment or black boxes, however, was very much on an ad basic due to the very rapid development and time scale pressures in wartime. Some very limited degree of integration between subsystems was introduced. For example, coupling the palm side to the autopilot, as you have seen the film Memphis Belle, maybe not. In general, however, as the system was standalone, systems and their integration into an overall system was carried out by specific crew members, such as navigator, bomb aimer, or radar operator. Okay? So let's go on. The 1950s period saw the emergence of a number of avionic subsystems, some of which were initiated during the World War II, which have since undergone continual development and now form part of the avionic equipment suite of most civil and military jet aircraft and certainly helicopters. For example, auto stabilizers or stability augmentation systems, ILS, VOR, DME, TACAN, Doppler, air data computers, attitude heating reference systems, or inertial navigation systems. The first major step towards integrating avionics systems was taken in the mid of 1950s with the establishment of the weapon system concept. These concepts were incorporated in the 1960s generation of aircraft, some of which are still in service. The concept requires a total system approach to the task of carrying out the mission effectively with a high probability of success. The aircraft, weapons, and the avionics systems required by the crew to carry out the mission effectively and must thus be considered as an integrated combination. It should be appreciated, of course, that the total system approach is applicable to any project, military or civil. As with many methodologies, however, military application provided the spark and the initial funding. The very widely used program evaluation review technique, or PERT, program evaluation review technique, networks, and critical path analysis, for example, were originally developed on the Polaris missile program. As an example of the overall system approach, consider the requirements for a naval strike aircraft. The aircraft must be able to operate from an aircraft carrier in all weathers and be able to find the target and attack it with a suitable weapon with a high probability of success. Operational analysis shows that to minimize the probability of detection and alerting the enemy's defense, the aircraft needs to approach the target at high subsonic speed. It's nearly 550 up to 600 kilometers at very low level at a height of 100 feet or so above the sea, so as to stay below the radar horizon of the target as long as possible. The avionics subsystem specification can then be determined from the overall system requirement, with an aircraft crew comprising pilot and observer or navigator. Hence, in the above example, the avionic equipment it would comprise radar or target acquisition in all weather conditions, Doppler accurate up to 4 kiloknots velocity sensor for dead recording navigation. But it should be noted, IN systems capable of accurate initial alignment at sea on a moving carrier were still under development in the early 1960s. Attitude heating reference system, or master reference gyro system, according to the UK terminology, is a attitude and heating information for pilot's display, navigation computer, weapon aiming computer, and autopilot. Air data computer, high calibrated airspeed, true airspeed, Mach number information for pilot display, weapon aiming, reversionary dead recording navigation, and autopilot. Radar altimeter, very low level flight profile during attack phase and all weather operation. Navigation computer, essential for mission. Autopilot, essential for reduction of pilot workload. Weapon aiming computer, certainly essential for mission. HUD, head-up display. All the advantages of the HUD plus weapon aiming for low-level attack. For example, toss bombing. Source management system, control and release of the weapon. Electronic warfare system, it means the radar phoning receiver, radar jamming equipment, all that essential for survivability in hostile environment. identification system, identification friend or for IFF, okay? Essential to avoid attack by friendly forces. Radio navigation aid, location of parent ship on return from mission. And communication radio suite, essential for communicating to parent ship, cooperating aircraft, etc. A significant degree of integration was required between the avionics subsystems. For example, the weapon aiming system requires the integration of the HUD, weapon aiming computer, AHRS, air data computer, and the radar system. The basic avionics system specified for a naval strike aircraft for service introduction in the 1960s. For example, the Royal Navy Buccaneer aircraft would also be required in 2010 up to today. Naval strike aircraft. The system would need to be of much higher performance, however, and there would also be additional systems in the next several years, which did not exist in early 1960s. For example, laser gyro INF, I hope you remember in one of our lectures, helmet-mounted displays, GPS, FLIR, smart weapons, etc. And a much greater level of system integration would be required. The aircraft would also be a single crew aircraft. The point being made is the essential continuity of the role of avionics systems and their development. Also, their implementation changes as new technologies become available. It should be stressed that although the above example is a military one, the same principles apply to the civil avionics systems too, in terms of their role in enabling the mission to be carried out safely and effectively with the minimum flight crew. Most civil avionics subsystems have also been directly developed from military avionics systems, and others say air data computer, INS, GPS, etc. And until recently, military aircraft generally required a large number of avionics subsystems with a high degree of integration. A major step towards facilitating the integration of avionics subsystems in civil aircraft was taken in the early 1950s and later. 10 years later, with the adoption of the INS specification for avionics system and equipment. INS is a non-profit making organization in the USA, which is run by the civil airline with industry and establishment representation, which defines system and equipment specifications in terms of functional requirements, performance and accuracy, input and output interfaces, environmental requirements, and physical dimensions, and certainly electrical interfaces. For example, air data computer, attitude heating reference systems, INS, communication radio equipment, data bus systems, etc. Equipment made to an INS specification by one manufacturer should thus be completely interchangeable with equipment made by another manufacturer to the same INS specification. Are you agree with me? Okay. The electronic implementation of the two subsystems can be totally different provided they conform to the IR-INS specification in terms of form, feed, function. For example, the LRU line replaceable unit must conform to the IR-INS specification dimensionally with the specified rack fixing arrangement, connector, and the pin allocation in the connector. The system must also meet the IR-INS performance and accuracy specifications and the environmental requirement in terms of temperature range, acceleration, shock and vibration, and EMC. The use of avionic equipment qualified to IR-INC specification, and thus ensures a competitive situation enables procurement to be made from manufacturers on a worldwide basis. I want to return back to early 1960s, where you can saw the development of the first real-time airborne digital computer. And these were progressively introduced in military aircraft from the late 1960s for tasks such as navigation, mission management, weapon aiming, radar processing, and displays processing too. These first-generation airborne digital computers were very expensive, and it is interesting to know that a number of proposals were made during the 60s to promote the concept of carrying out as many of the avionic subsystem computing tasks as possible with a powerful central digital computer. These proposals were not taken up for a number of reasons, such as vulnerability. It means all the eggs in one basket, whereby a failure in the central digital computer affected all the subsystems sharing its computing facilities. And second, inflexibility. It means changes in an individual subsystem could involve changes in the main computer software with possible ramification and knock-on effect on all the other subsystems sharing the computing facility. This was particularly relevant with the computing speed achievable at the time and the high cost and certainly the limited capacity of the non-volatile memory technology, which depended on magnetic core store. Typical store size were 8 kilobytes or to 16 kilobytes at that time. Imagine, I was starting to training in my Air Force college at that time. Third, cost and weight of redundant central computer configuration was unacceptable. The availability today, however, of affordable, very powerful processors with a large memory capacity and high-speed data buses has radically changed the situation. The concept of sharing avionic subsystem processing tasks between a number of processors with spare capacity to take over particular tasks in the event of a processor failure is now economically attractive. The integrated modular avionics architecture, which have been developed for the new generation of both military and civil aircraft, which entered service from around 2005 onward. In fact, explore this concept as will be discussed later. As stated earlier, many of today's concepts are not new. It is the technology available at the time which limits their economic exploitation. by the latter half of the 60s, the development of affordable task-oriented processors, that is, processors which are sized to carry out one or possibly two avionics subsystems computing tasks, had become viable with the development of integrated circuit technology. A number of avionics subsystems had thus been developed and were entering service in both military and civil aircraft by the end of the same 60s, which contained their own internal digital computer. For example, digital waveform generators in HUDs, air data computers, and inertial navigation systems. Many of the aircraft subsystems up to the early 70s, however, were still largely analog in their implementation, with synchro and potentiometer output and inputs requiring point. Means requiring point to point and wiring to interconnect them. The interface unit carrying out the necessary analog to digital, AD, analog to digital, and digital to analog, means DA conversion, to enable the subsystems to communicate with each other, which were inevitably bulky and could exceed the size of the digital computer. The complexity of the inter-unit cabling, looms, and wiring harnesses can be seen in this figure, which is typical of the late 60s or early 70s aircraft installation. But it should be noted that some of these aircraft are still being operated. The weight of the cable looms could be very significant and exceed several hundred kilos. The large number of multi-way plugs and connectors also inevitably degraded the overall system reliability and introduced intermittent faults. The first development to reduce the number of interconnecting wires was the use of time division multiplexing, TDM, time division multiplexing, of the signal to be transmitted between two units. TDM enables information from several signal channels to be transmitted through one communication system by staggering the different channel samples in the time to form a composite pulse train. Each signal channel is transmitted as a serial digital pulse train at a given time slot in a clock cycle, and thus, given the clock time information and the address of the signal, usually suitably pulse coded, the receiver can then decode and distribute the individual signal. Hence, if there are, say, 30 different signals to be transmitted between two units, wires are required in principle when the data is multiplexed compared with 60 wires. This type of single source and single link communication linked between two units, say A and B, is frequently referred to as A to B link. Early systems, in fact, used 3 screen-twisted pairs of wires to transmit the signal, address, and clock date. This was then reduced to 2 screen-twisted pairs of wires. Later, single and multi-source, multi-sync systems, however, operating at higher clock rates encode the signal data and address with the clock data using Manchester 2 biphase encoding, covered in the next module. I hope today. a single screen twisted pair of wires only is required with such an encoding system to transmit information data rate of up to 1 to 2 megabits per second. Higher data rates up to 100 megabits per second can be transmitted using a suitably screened coaxial electrical cable. And information at even higher data rate can be transmitted as coded light pulsing using a fiber optic cable. Today it's very popular now. By the mid-1970s, it became possible to implement many more avionics subsystems digitally, exploiting task-oriented processors and the newly developed microprocessor, and so eliminates the analog computing element and the analog input-output components such as synchros and potentiometer, and many others. It thus became possible to interconnect the individual avionics subsystems by means of a digital data bus system. This enabled the system to communicate with each other and transfer serial digital information using time division multiplexing in conjunction with a suitable protocol system to control the data transmission to and from each individual subsystem. This will be covered in the next module, but the dramatic reduction in inter-unit wiring can be seen in this slide, which illustrates the interconnection of the subsystems using a MIL STD 1553 data bus system. An essential parallel development in the late 90s and early 1980s was the implementation of the complex circuitry required by the MIL STD 1553. I mean that data bus system terminal in LSI and later by VLSI. This enabled the system complexity to be encapsulated in highly reliable IR chips with a chipset costing less than some multi-way connectors. The avionics system architectures, which had become established by the mid-70s, are still the standard architectures of current aircraft in service and are referred to as a federated architecture. Federated architectures essentially consist of a number of interconnected but functionally independent subsystems with some degree of central computer control of overall operating mode. The advance of digital electronics through the late 70s and 80s enabled the development of very sophisticated subsystems, which also still addressing self-contained functional areas, shared information via data link, such as, namely, 1553 bus. Federated architecture built up from individual proprietary design and available from a wide and experienced supplier base, became firmly established as the low-risk avionics system design approach. Also, because of the well-defined system boundaries and the clear division of area of responsibility, federated systems were universally accepted as the low-risk approach commercially and constructually as well as technically. In a federated architecture, however, there is inevitably some duplication of function in each of the individual subsystems, which makes the overall system heavier and more costly than necessary. LRUs are each designed and optimized separately, resulting in many different implementations of similar functions. Items such as processors, memory, software, interfaces, and power supplies are individually optimized for each subsystem. And the design and support of these unique proprietary parts drastically increases the overall system development and support costs. The subsystem design approach also limits the introduction to fault tolerance because the proprietary subsystems cannot easily share resources, and the cost of building redundancy into every subsystem is unacceptable. The use of proprietary subsystems also creates additional problems when an optimized proprietary subsystem interface must be accepted as part of an upgrade. The maintenance of federated systems is constrained by the proprietary boundaries of the architecture and requires the complete removal of subsystem black boxes from the aircraft for repair in second, third, and post-line maintenance facilities. Flexible deployment of such systems in military applications was seriously hampered by the need to deploy sophisticated second line for avionics intermediate shop support equipment. With the reducing numbers of new military designs, the need for mid-life upgrades focused attention on the high cost of upgrading federated architecture. Essentially, whole systems have to be removed and replaced, and a small improvement in system functionality, which can result in very large costs. Since the late 80s, avionics R&D programs in the USA and Europe have been directed towards finding a better way to build avionics. Over this period, the concept of modular system built from a small number of standard module types, housed in standard racking, and communicating over standard data networks has been developed and has become known as modular avionics. However, to achieve the full benefits from modular systems, it is necessary to dissolve the subsystem boundaries which exist in conventional avionics, so that a common pool of space resources shared between subsystems can be used to improve system availability. Hence, integrated modular avionic architectures offer additional benefits of fault tolerance and application flexibility through reconfiguration. Integrated modular avionics architecture has been accepted as the way forward for both civil and military avionics, and systems based on these concepts are now in service or will be shortly entering service. I hope you enjoyed this lecture, and I'm looking forward to seeing you next time to continue our favorite course. Okay?